Hi, in this video we are going to see about retarded potentials. Retarded potential. So the retarded potential refers to electromagnetic potential that account for the finite speed of light. In time varying scenarios, the potential at an observation point depends on the state of the source at an earlier time. This concept is fundamental for solving radiation problems where sources are time harmonic or transist. It is essentially a solution to the inhomogeneous wave equation, which describes how electromagnetic waves move through space. Radiation problems are often too complex to solve for electric and magnetic fields directly from current sources. Auxiliary potential functions, specifically the magnetic vector potential and electric vector potential, are introduced as mathematical tools to simplify these calculations. The standard procedure involves first integrating the source distribution to find the potential and then differentiating those potentials to find the actual fields. The retarded nature of these potentials ensure that the resulting electromagnetic waves propagate outwardly from these sources. To determine potential at a point located away from the source, a specific differential wave equation must be solved. For analytical convenience, the source is commonly idealized as a point source, which allows the potential to be expressed solely as a function of the radial distance from that source. In radiation problems, the mathematical solution selected corresponds to an outwardly propagating wave, ensuring physical relevance. This outward traveling wave solution confirms that electromagnetic energy radiates away from the antenna and propagates into the surrounding space. To find potential at a point removed from the source, a specific differential wave equation must be solved. For analytical purpose, this source is often idealized as a point source, which makes the potential depend only on the radial distance from the source. In radiation problems, the appropriate mathematical solution corresponds to an outwardly traveling wave. This choice of solution confirms that electromagnetic energy propagates away from the antenna and radiates into the surrounding space. In static cases, where there is no frequency variation, the potential reduces to a simple solution in which the effects are felt instantaneously through space. When the source varies with time, the solution differs from the static case by the inclusion of an additional phase factor. This phase factor accounts for the finite time delay or retardation required for the wave to travel from the source to the observation point. It is this retardation that enables independent wave propagation, allowing the electromagnetic fields to detach from the antenna and propagate freely through space. When the source is not located at the origin, the calculation of the potential must consider the distance from every point within the source region to the observation point. In such cases, the general form of the retard potential is obtained by integrating the current density over the entire volume of the source. This integral contains a specific term that explicitly represents the retarded nature of electromagnetic energy propagation. As a result, the potential observed at a given location and time is determined by the state of the source at an earlier time, reflecting the finite speed at which electromagnetic effects travel through space. A retard form of retard potential, known as the electric vector potential, is employed when magnetic current sources are considered. This formulation is especially important in the analysis of aperture antennas, including horns and waveguides. The solution for the electric vector potential is likewise expressed as an integral over the source volume and explicitly incorporates the effect of retardation. By using both the electric and magnetic potential together, the complete electromagnetic field in any region of space can be accurately determined. Retardation reflects the fundamental facts that electromagnetic fields do not occur instantaneously. Since electromagnetic waves propagates at a finite velocity, the field observed at a given distance is determined by the state of the source at an earlier time. If radiation were neglected, the theory would incorrectly suggest that effects could be observed before their cause, which is physically impossible. These inherent time delays arise directly from the laws that govern time-varying electromagnetic media. The derivation of retard potentials is given in this slide. The mind map for this video. In the far field region, where the observation point is very far from the antenna, the mathematical expressions for retard potential can be simplified using appropriate approximations. These approximations are valid when the distance to the observation point is much larger than the physical dimension of the antenna. Under these conditions, the retarded potential leads to specific spherical phase bonds for the radiated electromagnetic fields. The behavior confirms that at sufficiently large distance, the antenna effectively behaves like a point source from which radiation propagates outwards. Retarded potentials are the standard tools for calculating radiation from arbitrary current distributions. Without accounting for retardation, the theory of antenna would not accurately predict phase shifts or time delays. They provide a unified method to bridge the gap between stationary charges and dynamic wave propagation. They are the foundations for understanding how information and energy are transmitted wirelessly through space. Thank you.